we have our last invited, Stephen. So Stephen, who is an assistant professor in computer science at CMU. He's known for his work in ML fairness and differential privacy. He's the recipient of many awards, including an Amazon Research Award, a Facebook Research Award, and many more than my cash can keep. So without further ado, I welcome you. It's a true pleasure to have him speaking at PPAI.
Thanks, Sandal. Thanks for the invitation. Can you hear me and see the slides well, just to make sure?
Yes.
Thank you. Yeah, thanks for having me and inviting me to speak at the seminar. Exciting to be here and be able to connect with many of you. I kind of like this format to some extent, but I really want to invite participation and questions during and after the talk. So we have spent much of the day today talking about differential privacy. For this audience, I wouldn't bother to define this again. So we know after well over a decade of theoretical development, over the recent years, there has been lots of practical deployments across different organizations. Arguably, the largest deployment, which we heard about a little bit today in the morning by John about, is the deployment in US Census, but also happening across many commercial and tech platforms like Google, Apple, and Uber. So over time, more and more people who are not necessarily trained in differential privacy now have to work with differential privacy in their daily data and analysis task. So one of the questions we've been thinking about in our group is that how we can potentially facilitate these non-experts to work with differential privacy when they may not have a PhD in differential privacy. So one approach we've been exploring in tackling this challenge is to think about how we can generate differentially private synthetic data. So for example, suppose you have a sensitive data set. What we would like to do for the algorithm is not to release just noisy statistics or a noisy trained model, but rather we would like to release a synthetic data set, which you can think about as a collection of fake data records. So individual data record may look nothing like the original sensitive data, but somehow on a whole, the fake data set actually preserves some of the important statistical properties you care about. So we'll get into what sort of statistical properties you might care about in a bit. But the advantage here is that because the synthetic data set is already differentially private, you can safely just release the entire data set out to the world and also allow data scientists or social scientists to interact with it arbitrarily without further privacy concerns. So you essentially put very little limitations on what the data scientists can do and how they might interpret these sort of results. You can roughly think about different types of synthetic data release, and I like to organize it around two regimes, and probably they're not mutually exclusive, but it helps me to organize my thoughts. The first type of synthetic data we usually try to provide for some sort of query or statistic release. So oftentimes you can think about this regime as the data analyst or data scientist already have a large collection of statistics in mind. Okay, so US Census can sort of fall under this category. They already have a target set of statistics they would like to release every year or every 10 years, and they would like to release it through some synthetic data. The second kind was what some of us like to call general purpose synthetic data. So here the goals may be a bit more vague. Maybe you don't have like a predefined target set of statistics in your mind you would like to release, but you just would like to have some data on your hand to perform, for example, some sort of exploratory data analysis. Maybe you don't exactly have data analysis in mind to run, but you want to look at the data, look at the semantics or the basic distributional properties to come up with what sort of tasks you would like to do. Or more generally, you may want to run some kind of ML models, and the list goes on. but general purpose certainly may also capture releasing a bunch of statistics as well. So I'm going to use this two categories as some sort of roadmap to guide us through this talk. So I'm going to talk a little bit about our recent work for thinking about generating synthetic data specifically for query release or releasing a bunch of statistics that's sort of predefined and something you would like to get good accuracy. And then I will talk a little bit about maybe when the goal is not as clear, you think about general purpose synthetic data as well. And to maybe preview a little bit about the contents a little bit, a sort of emerging technical theme we'll keep revisiting in this talk and in a lot of our work recently is to sort of taking a somewhat unifying view, a zero-sum game view on synthetic data generation. So I view it as kind of a nice framework because it's quite intuitive and oftentimes allow us to recover some of the classical methods and allow us to connect these classical methods with some of the modern methods we would like to propose. Okay, so let me go into the first part where we think about how we synthesize privacy preserving data for statistical or query release. So let me first give you an example of what a query might look like. So I'm mostly going to focus on counting query. For the sake of example, imagine there's a medical database, just like the one you're looking at. So every attribute for now is Boolean. And a counting query is basically a simple form of statistic that asks what is the fraction of people in the data set that satisfies some specified property Q. Okay, so let me give you an example. You might want to ask what is the fraction of people that smokes and had lung cancer and has the OCD syndrome. So this form of query, you can sometimes computer scientists call it the three-way marginals, but really it's just a combination or intersection of three attributes. So in this case, you're going to evaluate this property on each individual record. And for this data set, roughly half of the individuals actually satisfy this property. So very simple. So the goal of releasing these kind of counting queries is to basically take a class of queries as input, and then you answer it, provide one answer for each query, and you want to be accurate. So we're going to say the set of answers you release is alpha accurate if the difference between the true answer evaluated on the private data set is alpha close to the set of release answers for every query. Good. So this is perhaps one of the most well-studied problems in differential privacy. Basically, you can track down the first paper differential privacy, and the basic problem we study is the problem of query release. So in this talk, we're mostly thinking about synthetic data, of course, and the way you're going to answer these queries is to actually come up with a synthetic database under differential privacy, and then you're going to use this synthetic data set to evaluate all the queries which produce all of this approximate or even noisy answers. So even though these are approximate or noisy answers given by a synthetic data set, one of the advantages you might really care about of taking this approach is some sort of statistical consistency, right? So if you, for example, count the number of people who smoke and have lung cancer and the number of people who smoke and have no lung cancer, these two answers will add up to the answer of the total number of people who smoke. Whereas if you take the more standard method like the Laplace mechanism and you perturb each answer individually, this sort of guarantee is not ensured. And this is the kind of consistency probably that is nice when you release the answers or release the data to non-experts so that they have a better time in interpreting these sort of results. So we're going to first focus on this problem. And before diving into the specific algorithms, I want to think about a rather general view of how to think about solving, or a general recipe for solving this problem, which is taking a somewhat zero-sum game view of this problem. Just as a preview, we're going to define a zero-sum game, and I hope that will be intuitive for everyone. Within this game, the equilibrium concept, we cover an accurate solution or accurate synthetic data set. And taking this framework has the advantage of allowing to design a set of algorithms or a family algorithms that leverage some of the online learning or machine learning tools called no-regret learning algorithms. And in particular, it allows us to reconfigure some of the established algorithm, which may be computationally very expensive. We can reconfigure this approach to actually get computationally efficient algorithms. And to mirror the title of the talk a little bit, the way we get efficiencies through some of the heuristic or powerful integer program solvers. Okay. So what is this zero-sum game? So I'm going to think about a hypothetical zero-sum game, sort of defined by the problem of synthetic data generation. So I'm going to introduce a game with two players. One of the players is called the data player. You can think about the data player playing some sort of data records in the data domain capital X. And also on the opposite side, there's a query player whose action is essentially selecting from the set of query class. You basically get to ask queries to the data player. So in general, we're going to think about a data player playing some sort of synthetic data distribution. So I'm going to interchange to use data distribution and data set to mean roughly the same thing. But basically, the data player get to choose some sort of distribution d hat over the domain X. And the query players at the same time can also choose distribution, but most of the time we think about query player just choosing single query to ask the data player what's the answer for this query. So this is a zero-sum game, meaning there is a single payoff function, and one of the player is trying to minimize this payoff, while the other player is trying to maximize the payoff. So we would like the payoff to sort of capture the idea of the error. So basically, if the data player is playing some sort of distribution d hat, and the query player is playing some query q, we're gonna define the payoff as the difference between the query answer evaluated on the synthetic data set and also the query answer on the true data set. So this is essentially a difference. So again, here, it will be convenient to think about the data player as someone who would like to minimize this objective, and the query player would like to do the opposite, which is to maximize. So for those of you who may be more detail oriented, you will notice that the U function, this payoff function, does not exactly capture the error, right? So in order to capture the error, you would like to actually put an absolute value around this, but we remove the absolute value. So one thing you can convince yourself quickly, or maybe not, is that if the query class is actually closed under negations, meaning for any query you care about in the class, the negation, the 1 minus q, is also in the class. So in this case, if you take the maximum over q for any given data set d hat, this maximum over q over the u function actually capture the max error of d hat. Okay, so but removing this absolute value actually help us to simplify the math quite a bit. But it's if you did notice that, it's not a super important detail for the talk. Okay, so for the zero-sum game, if the data player can select a d hat so that maximum over q of u d hat of q exactly equals 0, this means that max error of d hat is 0. So that you actually sort of provide a synthetic data set that perfectly match all of the answers. Of course, you don't expect you can do that because you're gonna have a private algorithm that try to approximate all the answers. But this sort of intuition carry over to basically approximate equilibrium. So in the zero-sum game I just defined, if you look at any alpha approximate equilibrium and look at what the data player is playing within the equilibrium, one can show that the max error, okay, so if you choose the worst query for d hat, the error is no more than alpha. Okay, so just some simple proof using the basic property of min-max equilibrium. What's nice about this, once you reach such equilibrium, you can just really release the distribution as your synthetic data. So your d hat just really become the synthetic data you would like to release. Now the question becomes, how do you actually compute such a approximate equilibrium or min-max equilibrium subject to differential privacy? So this is the sort of new constraint we would like to have. So there's quite a nice recipe, even without privacy, to compute such an equilibrium. If you're familiar with some of the literature in online learning, which is just a form of sequential decision making, there's a type of algorithm that solves this kind of game rather efficiently. It's called no regret learning. I'm going to briefly talk about it in the context of this synthetic data game. So you can think about this as a process that takes place over rounds. Okay, so I'm going to use little t to index rounds. And each round, sort of the data player is trying to sequentially learn a synthetic data distribution that minimize the sequence of losses given by the query player's historical play. So this is a repeated process, and at round t, the data player would like to update its synthetic data distribution to do well on what the query player has played so far. And after the data player has updated the synthetic data distribution, the query player, again, will try to criticize its synthetic data distribution, sort of trying to play adversarially by finding a high error query on the current synthetic data distribution. And the rounds will happen again, and the data player will update based on QT as well. So no regret sort of means the following property. I won't define it formally, but if you think about this sequential decision-making problems carried out by both the data player and the query player, you would like both of them to satisfy the following property. So they should suffer the cumulative payoff, which is not much worse than the cumulative loss of the best strategy. Sorry, the payoff should be lost here to pattern match. But what we would like to guarantee is that, for example, the data player is playing a sequence of synthetic data distribution and suffer the error picked by the queries from the query player. You would like the list of the sequence of losses to be not much worse had you picked the best synthetic data well ahead of time and fix it throughout the history. So obviously, you can always pick the true data set to actually minimize the total loss. The synthetic data play doesn't know such a data set. It's a simulated play, but the cumulative loss can be as small as 0 in our case. But overall, we would like the data player and the query player to satisfy this no regret property. And if you run this no regret learning dynamics long enough by some classical result from Horn and Shapiri in '97, you can show that the average play actually converged to an approximate equilibrium. So we're going to use this sort of no regret dynamics to compute our equilibrium as well. Let me pause here in case there are questions.
Well, I have a question right away.
Great.
So does this, you're essentially performing a repeated play, and
yep.
don't you leak privacy every time you're generating a new data sets from this distribution?
Yes, and I will talk about that. Yep.
Okay.
Yeah, thanks for the question. So let me talk about that by talk about how a prior algorithm works at that. So sort of established by now maybe 10 or 8 years old algorithms called MWAM, or private multiplicative weights. So to simulate this repeated gameplay by doing the following. So repeatedly, you're going to have the data player explicitly maintain a distribution over the domain. It's going to use an algorithm called multiplicative weights, or MW. If you don't know what it is, just think about it as a generic no regret learning algorithm. And the query player, after each round, the data player updates the distribution using MW. Is going to find a query with high payoff or high error using the exponential mechanism. So here, if you look at this repeated gameplay for your question, the only part that actually touches the private data is actually the query player. And we'll explain this a bit in a couple slides. So the only place that really depends on private data is the query player's optimization. It would like to find a query on which the synthetic data and the true data differs by a lot. So it actually touches the private data in some non-trivial way, and we're gonna use the exponential mechanism. So there are many nice things you can say about this MWAN algorithm. So the first thing is that we know it's statistically optimal. So if you want to answer a number of queries that's much larger than the size of a data set, this one really has the optimal accuracy or the sample complexity, depends on how you look at it. The main drawback of this algorithm, that the reason why we don't actually run this in many of the practical domains, is that this is actually explicitly maintaining a distribution over the entire data domain. So if your data domain have size or dimension D, you're actually maintaining a distribution of size at least 2 to the D. So because of that, no matter how smart you are about this, like this algorithm will be sort of running exponential in time, like even in the best case. And we know that there's some impossibility result that sort of says if you want to achieve this sort of statistical optimality or this type of bound, your worst case running time must be exponential in D. Your worst case running time has to be exponential in D. Otherwise, you will have an exponential, you have a efficient algorithm or polynomial time algorithm that breaks some cryptographic primitives. So notice that I'm actually trying to put italic around the word worst case. So which really just means we should not be providing provably polynomial time algorithm. But yet we should not give up on this, because we could still be providing potentially good average case algorithm that run fast on most instances. So this is where we introduce some of these ideas of heuristic solvers. So how do we overcome this computational bottleneck, right? So currently this MWAN algorithm is very established. Really, the bottleneck is coming from maintaining this huge probability distribution over the entire data domain. So one idea we try to leverage is that instead of explicitly maintaining this distribution, we would like to have the data player solving some hard optimization problem. So the hope is that while this optimization problem will still be worst case, very hard to solve, in practice, there are many sophisticated solvers, in particular integer program solvers like Cplex and Gurobi, that allow us to get at this computational bottleneck and actually give pretty good practical performance. So let me give you some example of how we take this approach. The first thing we did, this is by now an old paper. So instead of taking the ordering MWAN where the data player is running the MW online no regret learning algorithm and have the query player to do sort of what we call best response, finding query with high error, we're gonna swap them. And this is why this is called the dual approach. This paper is by now a couple years old, but it still captures some of the interesting ideas here. We're gonna swap the order, and instead we're gonna have the query player be the no regret player. So the query player will now actually run the multiplicative weights algorithm over the query class. So the advantage now is that because this distribution is over the query class, it's no longer over the data domain, this becomes a much more much smaller distribution to maintain for the query player. So you get rid of the exponential time from this left-hand side. The trade-off you get is that now the data player is solving the best response problem over a much larger space. So here you would like to find a data record from a data domain to minimize the payoff. This problem becomes intractable. Okay? But at the same time, it's actually a optimization problem. So let's look at this optimization problem in detail a little bit. In each round, you can think of the query players will provide a bunch of high error queries from the exponential distribution. We sample from it instead of presenting the explicit MW distribution for privacy, but it's not a super important detail. And what you would like to do for the data player is to pick a record to minimize the average payoff over the sample queries. So if you remember the exact payoff function, this is basically the optimization problem. If I exactly write down the sum of the payoffs across Q1 through QS, and the data player trying to minimize over the domain, so little x in capital X. So one useful insight that's also related to your question, Nando, is that if you look at this objective, the decision variable is X. And X, the little x actually is not going to affect all the terms that's associated with capital D, which is the private data set. So in some way, this Q of D across all terms is actually a constant within this objective. So one thing we know is that if you solve the optimization problem, the solution will be unchanged if you remove all the constants inside objective. So you can actually remove all the parts that's relevant or that depends on the private data. So this is essentially the optimization problem solved by the data player. In particular, this is a pure optimization problem, doesn't touch the private data, so you can solve it without privacy. In general, we know this is an intractable problem. It can be reduced to many well-established hard problems. And we know it's necessarily the case, otherwise we'll be breaking some impossibility results. But for many popular query classes we might care about, like K-way marginals, this is amenable to integer program formulations. So we can actually solve it by using integer programs, using something like C+ or Gurobi. Let me pause here in case there are questions. Okay, so this is sort of a dual approach and present this in this chronological ordering. So some of the recent work we did is actually take a harder look at this prior approach by MWAN, which you have the data player playing some kind of no regret algorithm like MW against some query player. So we would like to revisit this sort of primal view of how you solve this game. But now we know, since we know the data player is really the computational bottleneck with the online learning algorithm, we actually will replace this no regret algorithm, MW, by other no regret algorithms that can leverage different kinds of heuristic solvers. So if you're familiar with the literature, there's the type of algorithms that in expectation, if you take over the randomness, behave like multiplicative weights, but doesn't require explicitly maintaining a distribution using MW. Instead, they will try to solve optimization problems to generate sample from the distribution. So one of the recent work with my student Giuseppe Vietri, Grace Tan, Thomas, Mark Bunn, and Thomas Steinke, we tried to basically come up with a new algorithm that sort of replaced this computational bottleneck within the data player, the MW, by this type of algorithm called FTPL, follow the perturbed leader. And now each step is no longer about maintaining an exponential size object, but rather solving some kind of optimization problem. And we're gonna have the query player performing the same algorithm. So we're gonna use the exponential mechanism to sample queries. So the query players sort of stay fixed. Let me spend 1 minute to talk very quickly about what the query players doing is essentially solving a perturbed objective function. So this is the original problem that you would like to solve for the data player. This is sort of the best response. But instead of solving this, we're going to actually perturb the objective with some noisy linear term, which allow us to actually generate random solutions that behave like the exponential distribution. And this problem can be further reduced to something that is not solvable by the integer program. I think I'm running behind time, so let me skip the theoretical guarantees. The highlight is that we don't exactly match the optimal guarantee of MWAM, but we have similar guarantee, especially logarithmically in the size of queries, but we are suboptimal in terms of the dependence on the dimension of the data. So we ran some experiments with this. In particular, we mainly focus on this follow the perturbed leader with exponential mechanism and compare it with HDMM, which I think is a very useful algorithm and practical algorithm currently deployed with the census. And I have to be honest that HDMM is a really good algorithm. It's really hard to beat. And I think in a lot of regimes, HDMM, sorry, it means high dimensional matrix mechanism, is probably still the go-to algorithm. But what's nice about fan-model algorithm is that it tends to do better in regimes where you have stringent privacy budget. So if your epsilon required by the algorithm is small, in this case, we take adult in the loans data set and try to make it smaller than 1. Our algorithm will have better accuracy than HDMM. But if you increase the epsilon, the HDMM tend to outperform. One advantage of the FAM algorithm is also the nicer scalability with the workload. Again, for a smaller workload, here, I think HDMM tend to do quite well. But if you really squeeze the workload to be larger and larger, the type of guarantee FAM is good at, which is logarithmic in the query load size, start to kick in and start to have lower error. So let me skip a little bit about this and talk about the second part. Which is about thinking about general purpose synthetic data, but using deep generated models. So here you may not have the kind of statistic, the specific class of statistics in mind. So it's amenable of actually using more expressive models to represent the data distribution, like a deep neural network. So in particular, the kind of approach we explore here is generated adversarial nets. I think most of us would have heard about this framework. What's nice about this is really just another zero-sum game between two players. One is called a generator, whose goal is trying to mimic the real data. How it works is basically taking noise as input and try to spit out synthetic data that mimics the real data. And there's a discriminator, which is all solving some kind of classification problem. They're taking examples, either fake or real, as input and try to predict the probability that this input examples is real or fake. So since many of you have seen that, I'm going to quickly skip this part. So there has been a lot of recent work in the DP literature. Think about whether we can synthesize synthetic data by combining GAN and differential privacy. We have done some work along this line as well. We believe maybe we're one of the first work that tried this approach and did it in a case study of a clinical data set. But I think this line of work is growing over time. I won't be able to capture all of it. I think there's a little exciting heuristic and training techniques coming up in exploring this approach. I'm going to skip this part because it's basically tell you what the algorithm is doing in training a private GAN. But one thing we noticed in taking this private GAN or DP GAN approach, and I should be honest that a lot of hyperparameter tuning has to go in. Even then, I think this type of approach is very hard in the sense that there's lots of hyperparameter you have to optimize. And in general, GAN is just hard to train, even without privacy. And if you start training it with differential privacy, the noise will actually increase in stability. So one thing we notice is that if you give me any DP training algorithm, DP GAN training algorithm, it's actually producing a sequence of generator and discriminators over time. And the entire sequence of generator and discriminators actually satisfy differential privacy. Just the entire trajectory, not just the last one. And in fact, if you look at the last generator and think of it as a synthetic data distribution, it actually often provide poor synthetic data distribution because the algorithm may not have converged. But one empirical observation we made in this earlier work is that even though the last generator may provide poor synthetic data quality, there's actually some sort of mixture across these generators during the trajectory that provide pretty good quality. And this is actually a nice thing because you already spend your privacy budget in producing the entire sequence of generators. You might as well think about useful way to combine them to actually boost the accuracy. So we sort of take this empirical observation to sort of combine the GAN idea with the idea of boosting, or basically the idea of multiplicative weights. So again, the entire sequence of generator and discriminators already satisfy differential privacy. And what we would like to do is sort of compute a useful mixture over these generators. And I'm going to define sort of a post-GAN zero-sum game, meaning after you've done your GAN training, maybe it hasn't converged. You can still look at sort of restricted zero-sum games where you sort of have a set of generators playing against a set of discriminators. So here we're going to have the data player who get to control the samples from the generators, playing against a query player who get to control the sequence of discriminators, try to play essentially the same game that Wasserstein GAN is playing. So this is sort of the payoff function that govern this zero-sum game. But now everything is much more tractable because now the data player is only maintaining a distribution over a finite set of data. And the query player is only maintaining a distribution over a finite set of neural network. And you can actually tractably compute the equilibrium in this restricted game, unlike the original GAN formulation, where there is lots of non-convexity. So what we do within this framework is sort of can be viewed as an organic combination between the DP GAN approach and the MWAM approach we just mentioned, right? So here we're going to have the data player running multiplicative weights, but over a much smaller size object because these are just sample generated from the generators, and have the query player running exponential mechanism to select a useful discriminator that is also within the trajectory of the training process to discriminate against or give criticism for the data player to improve. And this allows you to actually compute an approximate equilibrium within this post-GAN zero-sum game. And the synthetic data distribution is now a mixture over the generated samples across all the generators. What's nice about this, you can also leverage the discriminator coming out of this equilibrium and use technique of rejection sampling to actually further improve this synthetic data distribution by sort of rejecting what the discriminator thing is, like the unlikely samples. So what's cool about this technique, what's nice about it we didn't expect is that it actually helped even without privacy. So this is an experiment, this is sort of a toy data set with 25 mixture Gaussian. So the top row, you're thinking about synthetic data algorithm without privacy constraints. So this is trained, everything here is trained without differential privacy. And what you can do is that you can essentially apply the same post-GAN boosting technique we provide to actually improve the sample quality over time. So one thing you can see is that the third column on the top row here is essentially after applying the post-scan boosting, which help you eliminate some of the unlikely samples. And this sort of rejection sampling technique we provide in the last column further refine some of samples better. Of course, in the bottom row with differential privacy, things become much more challenging because of the noisy training. So if you train the typical DP-GAN, so here we didn't use a very fancy neural network. This is what the data looks like in the last generator, which is a really poor approximation. But by applying this sort of post-scan boosting technique, you start refining the distribution that sort of look more like a mixture of several Gaussian. It's far from perfect, but it actually has a lot of improvement over the data distribution. So in this paper, we actually have some more experiments, which I don't have time to go through all of them. And because we're trying to think about general purpose data, we have a wide range of data analysis tasks, including performing basically all three-way regression tasks you may have. So you can pick out two attributes as predictive attribute and pick out one attribute as the outcome and use a two attribute to predict the third one and see how it preserves some of the RMSE score. So this is sort of the comparison between the RMSE score when you have the training on the real data, you're training the linear regression model on real data, and this is the training happening in synthetic data. And this is my co-author Marcel actually had this smart idea of how to present the comparison, but in general, you would like to see the lines as flat. And the technique that uses the post-scan boosting or along with the rejection sampling technique tend to flatten the line, which means the outcome of the RMSE tend to be similar. And we perform analysis on several machine learning tasks. Basically, you can try to train your machine learning models on synthetic data generated by either the standard DP-GAN or DP-GAN without a post-scan boosting technique, and with the post-scan boosting technique, and see which one actually achieved the highest accuracy on the holdout real data. And quite often the time, the post-scan boosting technique with the rejection sampling provides you with the highest test accuracy, which is nice. I think I'm about out of time, so let me quickly wrap up in case there are questions. So as a summary, one thing I like in thinking about these set of techniques or methods is that you can really draw somewhat like a unifying zero-sum game view on all of these algorithms. What's cool about this is that this kind of zero-sum game view allows to recover the classical methods like MWen, but at the same time allow you to reconfigure existing approach to turn it into more efficient algorithms that allow you to isolate a computational bottleneck and replace it with something that you can optimize for using heuristic solvers. So this is how we basically reconfigure the approach of MWen, and we design it to give algorithms like FAM or dual query. And another thing that's nice about this zero-sum game view is that you can combine the classical methods like MWen and differential privacy with some of the more recent deep learning approaches. So in particular, this method we cover at the end I can view it as some sort of organic combination between the DP-GAN and MWen. Both are taking this zero-sum game-like view. So I feel it's quite natural to combine them together. So let me pause here. Most of the papers are on arXiv except for the first one, but you can check out the first paper in Terrence's poster session. And other papers, except this paper is on bioRxiv, not on arXiv. Everything else is on arXiv. And I look forward to further discussion now or later through email. Thank you.
Thank you, Steven. That was a really nice talk on this perspective of game theory and data release processes. So I'll start right away by reading some of the questions that are coming in. So the first question by Christine is, do you have any interest in joining the current NIST challenge?
Yes. Short answer is yes. And it's been rough couple weeks in terms of conference deadlines. So it's something on my to-do list. One thing that we've been interesting about the upcoming NIST challenge is that it's all actually using the ACS data. Yeah, so and we've been running some experiments with it too. So that will be very cool for us too. Yeah.
Great. So I guess meanwhile the audience warms up, I'll have a couple of questions actually. So the first one, well, just a comment from Christine. I would love to have you, but you got a week or so to go.
Okay, I should get back to work now.
So I was very intrigued by actually both parts of your talk. So about the second part, so you use this mixture of generators, and you're saying that they are providing some usefulness, right? And do you have any intuition why? In a sense, is that they are characterizing different regions of distributions, or in your example, actually look like that you're looking at the intersections of those distributions that are characterizing. So do you have any intuition why it is that using this mixture here gives you such better?
I see. So this is the picture you're talking about.
Yeah, exactly.
Yeah, that's a great question. Thanks. So I would say that your intuition is probably capture a lot of the phenomenon that's happening, which is what people working in GAN call the cyclic behavior, where the GAN is, if you look at the trajectory of the different GANs that are being produced, maybe each generator during the trajectory is capturing different parts of the data distribution. And I think this is a valid empirical observations. And yes, we are leveraging that and try to take the mixture. So in this case, maybe even this may be not the most representative example to capture your observation, because the last generator actually captured sort of a superset of the data distribution you care about. But what this boosting technique is doing, I think, is actually take sort of this type of data and do reweighting using the set of discriminators you already have to downweigh some of these middle points that are less likely. So it is taking a superset of the data, but also doing smart downweighting on data that are unlikely, especially this rejection sampling technique. So maybe that's a way to interpret the empirical finding. Yeah.
But in a sense here, you could play two ways, right? Either by acting on the GAN itself. I mean, you could modify the GAN training itself to generate more disparate distribution. If this is really what helped your algorithm.
Yep.
Or like you're doing in the objective of your post-GAN approach that picks up those, cherry picks those distributions here, right?
Definitely, yeah. Yeah, that's a good idea. I think like this objective we essentially inherit from somewhat standard formulation, but there are things you can encode, like encourage diversity across generators, things like that. That might be helpful for the training. Yeah.
Yeah, if that was paying off. So any question from the audience? So I have an additional question about your first part. So this is interesting because essentially you're using here optimization for generating this set of queries, and you don't even care about the data. So in a sense, that results to be independent, right? As
yes, this is a part that
But does that help you? I mean, would it help you to use some data distribution, some public information, to generate a set of subset of queries that might be more relevant? For instance, by adding constraints on the queries that you can generate.
So let me understand the question. So you're thinking about like using like public data or prior information.
Priors, exactly.
To choose smarter queries.
Yes.
Yes. So we have taken this approach. Actually, that's like where I try to have a plug for this bunch of slides. Yes. So The short answer is yes. Potentially, you can do smarter selection of queries. Actually, more generally, you can have smarter algorithm that somehow leverage the form of public data to have to actually train this kind of synthetic data distribution. This is actually another paper in this workshop. I believe my student Terrence is giving a presentation in the poster section. He had the spotlight talk this morning. So this is an ad for him. Yeah, but in general, I think leveraging this kind of prior information is a very promising approach. I I don't get to talk about this, but I think this is maybe the way to go for many of the synthetic data tasks to leverage this kind of prior information. Yeah.
Mm-hmm. Okay. Well, thank you. So any other question from the audience? All right, we have a shy audience. This we must do the post
It's a
line.
long day.
But I'm sure that they could probably reach you in other ways if there are other questions. Well, Sten, thank you once again. That was really a lovely talk. I really enjoyed it, and well, we'll hope to take the discussion further. But time is up, and we'll need to go to the poster session. So thanks again.
Thanks, everyone.
Virtual round of applauses. And mine was not that virtual. Okay. So for the audience, the poster session is moving to Discord. So there's a link on the conference webpage. You can join the Discord channel, the Discord server. There are several channels, as I mentioned this morning. So each paper is associated with 2 channels, a text channel where you can ask questions, see a short video presentation and the poster, and then the authors that are participating in the poster sessions should be in the voice channel, so you can ping them and ask query to them directly. So this section here, this part actually concludes the PPAI tutorial for today. We'll move to Discord for now, and then we'll see each other again tomorrow morning at 9 a.m. for the next speaker in the next part of the program. So thank you, everyone, for your participation. Thank you, Stephen. Thank you, all the participants.
Thanks.